Alright, this is question 6 from your practice question 2009. Alright, it states that the feedback control loop is shown over in this diagram, and then therefore show the Nyquist stability criterion, and under which condition does this criterion apply. Alright, so you may wonder, how do I use this thing to illustrate the condition for the criterion, and therefore I also don't know why. But anyway, the Nyquist stability criterion is actually from your page 22, you can check it out. Alright, you know two things. The first thing is the standard Nyquist stability criterion, and then a generalized Nyquist stability criterion. Alright, you have to really understand how this works. This one, for this sake over here, what it means is that you assume that the loop gain L0 has no right half plane pose. Alright, open loop stable. So what it means is that you have a open, this is the S-plane, this is not your Nyquist plot, okay? The S-plane itself, alright, this is the right half plane, alright, normally indicated by this contour, because this is a Nyquist contour. Then once you plot this contour, you'll create a Nyquist plot. Alright, but anyway, now we have a open loop stabler, right? Because all the poles are open loop over here, are in the left half plane, so it's stable. So once you close loop, ensuring that the poles doesn't move towards this side, or if this towards this side when you close loop, this means that you're unstable. So however, if you were to move over here, then this is still stable, still okay, then it stick, it is good. And therefore this, when you plot this contour for the closed loop, when you plot it in the Nyquist plot, alright, over here, maybe I should use a different color now, then you have a -1 over here, then Nyquist plot may be somewhere over here, so you should be safe. Alright, so in the standard Nyquist stability criterion, it says that the poles are always on the left half plane, open loop or closed loop always at the left half plane. Alright, but what about the Nyquist stability, the generalized Nyquist stability criterion? This is sort of a lenient way to use the stability criterion, because it's not very strictly defined as per this. Why do I say so? It's because, as you can see, this is the same contour. Alright, I mean, I should label it as an open loop. Alright, you can allow your open loop poles and zeros all to be here. Okay, in this case, you can allow your stuff to be here. This is called the open loop unstable, but we don't mind. Later on, you'll know how does this works. But once you close the loop, okay, normally you wouldn't know how to define the closed loop, how many zeros and poles, alright, because of certain stuff. But I just want to convey is that normally when you want to determine the number of closed loop poles and zeros, you require two things. The first thing is your Nyquist plot. Alright, in this case I have a -1 over here. Alright, I encircle this -1 2 times. Alright, I encircle 1 time and encircle 2 times. Alright, so far so good. So therefore I am encircling in a clockwise direction, anti-clockwise direction. Alright, so I encircle 1 time, 2 times, and in a anti-clockwise direction, and therefore n is equals to -2. Okay, which is this n over here, the number of zeros. This n tells you not the number of zeros, the number of encirclement on -1. Alright, this may be new to you, but please go and watch the Nyquist stability playlist if you want to know more. But this is just the understanding of it. Alright, and why is it negative? Negative is because I'm going in the anti-clockwise direction. If it's a clockwise direction, as like this, going in this clockwise, then the n is equals to 2. Alright, and therefore this thing you need to know is that for the encirclement part, the number of n, you need to know how many encirclements are there. First thing, in this case is 2. The next one you need to see is it going the anti-clockwise or the clockwise? If it's clockwise, then it's +2. If it's anti-clockwise, then it's -2. Alright, so far so good. The next thing after that, you need to know your number of poles. The number of poles comes from your transfer function g of s is equals to u of s over y or whatever thing lah. So you need to take the poles, and then you calculate the number of poles that is within the closed loop. Alright, that's why I highly recommend, because why am I having this? Anyway, so because maybe this is some y of s lah, for example, maybe this is y of s over u of s. This is your input. or your input u of s is equals to maybe some s squared plus blah blah blah, and then at the end of the day you may have 2 plus 3j, and then minus 3 s minus 3 s plus 3, something like that. So you have a something like a 3 poles. Alright, at this portion over here you need to know there is one real number. As you can see, there is imaginary and real. So this real number is simply telling you that the location of your closed loop poles is already at 2 plus minus 3j. Alright, so from here you can gather the information from your closed loop poles, stating that there is actually 2 poles that is in the right half plane. While this one s plus 3, the roots is actually at the minus 3. So we actually don't care about this thing. We doesn't include this thing. So at the end, in here over here, since we know there is 2 poles over here, we can say that is p is equals to 2, because there is 2 poles within the right half plane. So therefore, this is the understanding that you need to know also. Alright, so it's not directly plotting out telling you the Nyquist plot or whatsoever. Yeah. Therefore, since we know that our p is equals to 2, alright, so therefore minus 2 plus 2 is equals to 0. And therefore this one is simply telling you the z. Alright. And for the generalized Nyquist stability criterion, you have to ensure that your z is always smaller than 0, smaller or equals to 0. Alright, so in this case it's 0, this means you're stable. Alright. If you have z like minus 1 or minus 2, then you are still also considered stable. Unless your z is equals to 1, 2, 3, whatever, then you are considered unstable. So this is the key differences between your Nyquist stability criterion and your generalized Nyquist stability criterion. You need to know this. And this is also the last sentence. It says that the number of anti-clockwise encirclement of minus 1, just now we know that there is two encirclements that is going the anti-clockwise around minus 1. Alright, is equals to the number of p, the number of poles in the right half plane. And just now we show the closed loop poles, there is 2 poles over here. So n is equals to minus 2 from our Nyquist plot, and we also have a closed loop poles from our transfer function p equals to 2. So when you add it up together, z is equals to 0. Alright, so therefore this is somewhat very super summarized sentence to illustrate this particular meaning over here. Alright, so be very careful about this thing. And therefore, how do you answer this question? Under what condition does this apply? Because what I've shown you just now all along is just explaining, and in fact the answer given is also telling you this. But what's important for this answer, I will highly believe, I may be wrong still, but is that we're talking about this figure over here. Alright, because as you can see the transfer function over here, alright, this transfer function is talking about the plant, the disturbance, and the noise. Alright, so the inputs may be open loop, unstable, maybe have poles and zeros over here. Alright, the plant also may have poles and zeros over here. Alright, because you will know that after so much thing, we know that the controller somewhat controls the plant's instability. Alright, or we use the word compensate. Alright, compensate for the plant's instability. So when the plant is unstable, this means that when it's open loop unstable, there is poles and zeros over here. You need to use a controller to close loop the plant, such that when you close loop the whole CP, alright, you have no poles and all your poles and zeros on the left half plane. So that in the right half plane is kind of safe. Or you may have a poles over here, and the Nyquist plot encirclement and things like that, which is talking about z equals to m plus p. Alright, so ensuring that you follow this Nyquist stability criterion, you should be safe, right? Hence and therefore, I will highly believe that we're talking about the generalized Nyquist stability criterion for this question. Okay, and therefore you can allow your CP, your closed loop gain to be encircling 2 times on -1. Alright, and then ensuring that it's anti-clockwise and it's equals to the, I think you get what I mean already lah, because if it's -2 plus 2 poles, then it equals to 0, things like that. So your number of encirclement in the anti-clockwise direction, this is negative, means anti-clockwise, plus must be equals to your number of poles in the right half plane, in your closed loop half plane. Alright, it's not necessary to be 2. You can be 1, you can be 0 also. 0 will be better because this means that you're very stable, not in that sense, but rather than you're still stable, because negative 2 is still smaller than 0. Alright, and therefore we can still say it's stable. And these are the things that you really need to really know. Alright, I hope that this is clear. And the next thing I just want to convey is that I don't even know what the hell is this talking about. So if you next time free, you understand, then you check it out. Alright, and therefore this is a understanding for this question on question 6. So I shall see you in the next video for question 7 and 8. Alright, hopefully I can, anyway, see you there.